Alright, so yes, the stress equation is sigma A, as you can use sigma 1, 2, is equal to sigma x over 2 plus square root of sigma x over 2 squared plus tau xy. So there's normally a sigma y included here, plus sigma y and then minus sigma y. But in the plane stress diagram, sigma y is actually equal to 0, so we're going to ignore that. So sigma y is equal to 0, which allows this equation to reduce to this. So then using sigma x, excuse me, we end up with 499.34 over 2d cubed, this is negative, plus all this stuff over here, and then moving on, which then goes to equals negative 249.67 over d3, 249.67. 249.67. Sorry about that. Plus square root of doing all this math up here with the numbers that we had earlier. 62335.11 all over d to the 6 plus 28247.52 all over d to the 6. Okay, so that makes sigma A equal to negative 49.67 all over d to the third, plus, doing all this math in here, gives 300.97 all over d to the third. You can just put that in your calculator and you'll get the answer out. And well, a little bit of mental math, but it's not the big of a deal. And then adding these two together is equal to sigma A is equal to negative 550. Oh, sorry. Moving on to sigma B already. That's not right. Sorry. Is equal to 51.3 over d to the third. That looks better. Newtons per meter squared, because those are the units of stress. And if you go through the units here, you can see how they change. But the square root and all this other stuff, squaring going on, just makes units hard, so I kind of ignore them a little bit. So going on with that, and then sigma B, you can skip a few steps here because you know it's going to be almost identical, except this is going to be a minus sign. So then you've got negative 249.67, doing this reduction all the way down through there, over d to the third, minus all this math in here, which remains the same again, 300.97 all over d to the third. So then sigma B is equal to negative 550.64 all over d to the third. And these are your principal stresses, this one and this one up here. Oops, sorry, totally didn't let you guys see that. So, as I said before, reduction up here, going on, moving along like that, all happy times. And then bringing this number down here again, bringing that number down here again, and then just putting a minus in here. All the other math remains the same. And then you get your other principal stress. Alrighty, so now, moving on. I'm going to start a whole new page here. So, I'm going to go to the next page there, alright. Clean that all up. So, brittle column Mohr. Brittle, or Coulomb Mohr. Coulomb is actually an electrical scientist or physicist who did all this stuff. So some professors will pronounce it Coulomb or Coulomb, whichever one you want. Okay, so we're finding the diameter. As you could see in the previous chunk of stuff that we did, sigma A and B are in terms of diameter. So we're going to solve for the diameter now. We know that we have a factor of safety equal to 3. Diameter equal to question. Okay, and we saw earlier that the material was cast iron, so we know it's going to be brittle. So this is brittle column Mohr theory. You only use column Mohr for brittle materials. It's called brittle column Mohr, but sometimes you just call it column Mohr. Okay, so for cast iron, a few material properties of cast iron. These are coming from the Shigley book, Shigley Machine Design. E is equal to 100 gigapascal. So giganewtons per meter squared, which comes from table A5 in the back of the book. And then from A24, the ultimate strength is equal to 552.5 KSI. It's only in KSI, so you have to do conversion, which is equal to 3.62 times 10 to the 8th newtons per meter squared. And then SUC is equal to 164 KSI, which is equal to 11.32 times 10 to the 8th newtons per meter squared, which again is Pascals, or in this case it'd be almost gigapascals. You can't see that again, the camera's all out of focus. Sorry, I'm using a cheap webcam for this, so if you can't hear or see very well, I apologize. Okay, so moving on with that. Using the conditions of Coulomb Mohr, I'm not going to go into those, but we know that. Oh, excuse me. Actually, I'm going to go back to this sheet, this other sheet, to do this. So I know that sigma A is greater than 0, which is greater than sigma B. So within brittle column Mohr theory, this is case 2. So we'll be needing that here in a second, which comes over to here. And then in column Mohr theory, we see that within case 2, the equation is sigma A all over SUT minus sigma B all over SUC, which is equal to 1 over N, which is your factor of safety. I know I used FS up here, but it's interchangeable between N and FS. So then, plugging in all those numbers, we get 51.3 all over B cubed times SUT, which is equal to 3.62 times 10 to the 8th newtons per meter squared, minus, I'm sorry, I'm terrible at units. If you're another person who just doesn't care about units, then you will enjoy this. If you are someone, I don't usually use units very often in my calculations, except to keep something straight in my head. Units are really handy to solve a problem if you don't know where you're going, because they can kind of lead you to a solution, but in something this complex, they mainly just take up space, which is equal to 1 over 3. And this was SUC, which I got from the book. Okay, and then all this stuff solves down to 14.17 times 10 to the negative 8 all over D cubed plus 48.69 times 10 to the negative 8 all over D cubed, which is equal to 0.33. Okay, and then solving that out, 14.17 times 10 to the negative 8 plus 48.69 times 10 to the 8 negative 8 is equal to 0.33 cubed. So I'm actually showing you the algebra on this because this is the important part of the problem. And then 190.48 times 10 to the negative 8 is equal to d cubed. So 0.012 meters is equal to d cubed. But we want it to the nearest millimeter. So it's 12.4 millimeters is equal to d. Sorry, not the cubed, just d. Alright, there we go. And if you want to round it up, that would be 12 millimeters is equal to d. So I'm going to use 12.4 just because that's nicer, and we actually need that in the next part of the problem. So that was brittle Coulomb Mohr. Now moving on to modified Mohr. In modified Mohr, the equation that you use is sigma b all over sigma a, absolute value. And then doing that calculation, I'm actually going to label this modified Mohr. Mohr went off by himself and figured this one out. So we're going to do that. So this is equal to negative 550.64 all over d cubed all over, that was sigma b, 51.3 all over d cubed. And now just by basic algebra, we know that those cancel and that one cancels. And then doing this math, this is equal to absolute value sign, big absolute value sign, is equal to 10.73, which is greater than 1, which now leads us to the modified Mohr equation that we're able to use, which is equal to SUC minus SUT times sigma A all over SUC SUT. I'll bring that up there a little bit so you guys can actually see it. Minus sigma B all over SUC. I know I'm switching between capital and lowercase letters on these, but A is A and B is B. We're not that specific with the variables in this case, so just bear with me on that. 1 over N. I'll say N right now, which is the factor of safety. So then, reducing all of this, we end up with big nasty thing. It is 11.31 times 10 to the 8 minus 3.62 times 10 to the 8. Oh my goodness, this is a hard one. And then sigma A is 51.3 all over d cubed all over 3.62 times 10 to the 8 of 11.31 times 10 to the 8 minus negative 550.64 all over d cubed all over 11.31 times 10 to the 8. And Newton per meter squared, just a E annoying there. And then 1 over 3, because we still have a factor of safety. Now, going through and doing all this stuff, we end up with 39.4.5 times 10 to the 8 divided by d cubed all over 40.94 times 10 to the 16 plus 48.69 times 10 to the negative 8 all over d cubed is equal to 0.33. Okay, and then solving this out, 9.636 times 10 to the negative 8 all over d cubed plus 48.69 times 10 to the negative 8 all over d cubed. Again, showing all my work here to you guys. Showed all my work in the rest of the homework problem. In engineering, it's very important to show your work because if someone can't understand it, especially your professor, they are going to yell at you and take points off. So do a good job on that. Show infinite amount of steps. And plus, when you come back and study later, it'll be a lot more helpful. 0.33. As you can see, these two powers are the same. They should be pretty close to the same so that you get a realistic number. If this one's way out of whack, then you may have missed like the 16 up here or the 8. I actually did this the first time I was working this problem. So just watch your powers of 10 up there. So we get 9.636 times 10 to the negative 8 plus 48.69 times 10 to the negative 8, which is equal to d cubed is 0.33, which goes to 29.3 times 10 to the negative 8 plus 147.54 times 10 to the negative 8 equal to d cubed. And then solving that all out, you get 12.09 millimeters. There I skipped some steps, but they were shown in the last steps. You know what I all did, what we did. Okay, so that was the modified Mohr diameter. And from that, within this discussion, you can see that the diameter is half a millimeter smaller than the one we got from Coulomb Mohr, the standard Coulomb Mohr. So you can see that Coulomb Mohr is actually a more conservative theory because they require more material in order to stay within the same factor of safety, whereas modified Mohr gives you a little less leeway there, a little less material to work with because it's a lot more, it's a lot less conservative thing. It's a lot less conservative, so it thinks that you need less material for the same amount of strength that the Coulomb Mohr does. And there you go, that's modified Mohr and Coulomb Mohr. See you guys.